Good afternoon, everybody. I'm a new PhD student, first year PhD student. I'm working under the supervision of Professor Uwe Tuzun, and Skelton, DM Has, and Kurt Quendon. My topic is structure formation by migration of particles in suspension flow. Here, I'm just defining what's the migration of particles, so everyone know what's migration of particles in a dense suspension. Migration of particles has a great importance in the dense suspension flow. There is a lot of work being done by this. Here I'm going to do some simulatory work on this. So this is my picture which shows my work. I'm doing just the simulatory work on this one. The particles, I'll start first my work with the MD method, and that's molecular dynamics, and then I will go further to a DEM method. First, I'm checking the particles here. Either they migrate from the high shear rate to the low shear rate, that is the center of the channel, under the boundary condition. And there will be some force, influence some force. Experimental work being done by different school of thoughts, but here I'm just presenting one example of Morris. He gave these examples and shows the flow rate of, as the flow rate is higher, for example here is 0.125, 0.25, 0.5 and 1. So it shows the migration of particles, where these particles are solid particles. So my presentation outlook is like this, and I will first present the industrial background and then theoretical background and so on. So migration of particles has a great importance, as we know. So the industrial companies, sorry about this is my first time, so I don't know how to do this. As like these companies, Procter & Gamble, Dow and Unilever, GSK, and etc. So these have the lubrication interactions, and the particles where the Brownian motion is considerable, and they consider the low Piclet number. So for the high productivity, so good quality of product, they're considering the low Piclet number. Like for example, we can take the healthcare, food and pharmaceuticals. Like these are the pants and etc. For the high productivity, we need small particles for the low Piclet number. So Piclet number, it is the ratio of the time required for the Brownian diffusion to move its particles of its own size to the time required for the shear flow to move it with the same distance. Piclet number depends on the temperature, the shear rate and the viscosity of the fluid. For large Piclet number and low temperature, the Brownian diffusion is not relevant at this time. The Brownian is not relevant this time. So for this, to support my study, I'm going to show my theoretical background. I studied the theoretical background, and I found out the three types of models. One is phenomenological models, the second one is granular temperature models, and then isotropic models. So phenomenological models based on the collision mechanism and viscosity mechanism, Barrington and Akravis and Phillips. Collision mechanism depends on the particle migration, which particles interaction. sorry, not particles interaction in a suspension flow. So when they collide, the momentum take place, but they will collide, and the collision will happen when they are rough, according to Jacobson and Kundert, that when they are rough, then the collision will happen. And they also present the viscosity gradient mechanism. Viscosity gradient mechanism is based on the particles suspension, it's based on the suspension viscosity, which is due to the particle volume friction. These models are just for pure shear flow and high Peclet number, but we are interested in low Peclet number. So this gives me a background of the Peclet number and the phenomenological models. Here I have taken this picture from Wahid thesis that it shows for high solidity and according to the half of the channel. So the first one, so that Kc or K mu, where Kc is the collision mechanism constant and K mu is the shear viscosity mechanism constant. So the ratio between these two shows the different curves. Granular temperature models. Granular temperature models also like McTague and Jenkins 1992 and Nutt and Brady, they presented these models. They presented an extra field, an extra temperature. They showed that if the particles move around one another, so they need to go further, and for that purpose they said that there is work done, and that named this granular temperature, and they present extra balance equation and Fourier heat conditions law, and they did this one for boundary conditions, which is McTague and Jacobson did this for smooth boundary conditions, and Nutt and Brady did simulatory work on this. This shows the boundary condition K, this is the boundary constant. Anisotropic models, Morris and Bolin and Stegelt, that presented the anisotropic models, and anisotropy is the mean of particle distance to obtain an extra stress component normal to the viscosity direction constant. After this, it would seem that the granular temperature theory is most easily adapted to study the effect of Brownian motion in smaller particles. So we will study the granular temperature to imitate the Brownian motion of smaller particles. So for this, I just started my work, and I did my plan like this. First, I will do the molecular dynamics method, and then go further step over the DM. So I started the molecular dynamics method, which is the time stepping method, and based on the classical mechanics. In this, we are going to using the Lennard-Jones potential for particle-particle interaction, and going further to find out the properties of each particles at each time step. Then we will go further on the discrete element modeling, and this is also based on the classical mechanics, but I will say that this is the power set of the all numerical methods, because in this one we can take the soft particles, rough particles, any type of particles to simulate and large systems, and we can find out different properties that what's going on in the channel. For example, the Stokesian dynamics and Brownian dynamics, etc. So I will study the rough particles using the DEM method under the lubrication interaction. So I have taken this one from Jenkins and Kunder's papers, that these are the rough particles which show like this, and I will find out the Brownian motion in the suspension. Then we will study after this the two-phase system, which will be based on the molecular dynamics and the discrete element method. And we will find out the lubrication interaction of the small particles and the solid particles. As I did my current work, so first I did my MD simulations using the Leonard-John potential and equation of motion by using the leapfrog step method, velocity distribution function, articulation function, and find out the diffusion equation as well, diffusion function as well. And then I find out some plot which shows the kinetic energy at each time step of the particles, of each particles at different each time step, and then the potential energy which shows the particles potential energy, the same thing at each time step, and the total energy, temperature, and the pressure. And I am going further to find out the velocity profile, which will be like the Poisson profile. And so these are my conclusions. Study of particles, I just did these things, but I need some feedback from you people to help me that how to go further in this. So please help me.
Thank you. Yes?
You might look at a paper by Frank, Journal of Fluid Mechanics a few years ago, which is an experimental study of the same problem, the effects of Brownian motion.
All right.
The question? I didn't get how do you introduce the hydrodynamic interaction in your molecular dynamics?
Sorry.
You have the Leonard-Jones interaction,
Yeah.
but the hydrodynamic interaction through the fluid, you have them or in your model?
Hydrodynamic interaction.
Yes.
No, I didn't introduce, but
Or the ones that are not
hydrodynamic force on the boundary walls, just to make the oscillation, we need to fix those walls and just to find out the interaction of particles inside the channel.